Hello and welcome back to Calculus 2 section 6.7 on physical applications, meaning word problems in physics. Now we are going to talk about a couple of concepts. The first one is the concept of mass, which I like to describe as quantification of physical existence. If you can touch it, if you can punch it, if you can lift it, right? If you can drop it, it has mass. If it exists in physical realm, it has mass. Then we can measure it. The mass doesn't depend on gravity in any way. The weight does. Weight is force. Mass is one of the basic physical phenomena, which is the basic physical property of objects that exist in physical realm. Thought does not have a mass because it doesn't have its physical manifestation, right? It's something abstract stuck in your head. Love is another one of those things, right? Feelings, right? However, if you are talking about a ball or a car or a person, right, you can talk about physical existence of that object or a person, right? And that would have a mass. Now, mass is going to be given by density times the volume, because the mass has to occupy space. Yes, the speck of dust is very, very tiny. It has very little mass in comparison to other things we know of, but it still has mass and it still occupies space. Regular expo marker, my pre-calculus students measured it for their project at one point, is 16.2 grams of mass. So those regular expo markers you see all the time, 16.2, right? Body weight, right? The normal size human, like 60, 70 kilos, kilograms, 1,000 grams, that's a mass. Right? Now, obviously, you get much heavier than a person, like a truck or a train, right? Would be sometimes measured in tons, right? So we start with the Precalculus formula, which says mass is equal to density times volume. So what is heavier, 1 kilogram of lead or 1 kilogram of feathers? It's the same. But hold on, I need a couple of trucks of feathers, right? And I can probably put a kilogram of lead. It's just going to be a little nugget, right? A kilogram of lead. I hope you see density times volume at work there. Feathers, they're not that dense, right? You can poke the finger to the feather, you can bend it, you can break it, you can strip those little, right, feathers, right? Each feather, you can destroy it, like, don't even think about it, right? Not dense. Not dense at all. It's going to occupy a hell of a lot of volume to make 1 kilogram of feathers. That's going to be a lot of pillows, right? Kilogram is about equivalent to about 2.2 pounds of stuff, right? 1 kilogram of lead. That's going to be fairly small. Lead is very dense. Heavy, right? Very dense. You can't poke finger through the lead, right? You can't mold it with your fingers and so on. Lead is going to be very dense and the volume is going to be very small. So I hope you see the game of density versus, right? Then we can talk about density of water versus density of concrete, right? And then which one is heavier for the same amount of volume. If you cut out a certain size of concrete and then you take as much water, right? Well, now the volume is the same, right? The density of the water, the density of the concrete, way different things. Clearly, the mass, right? If you can hold this much water in a water balloon like that easily, right? It's going to be much tougher to hold this much concrete, right? I mean, obviously not a problem for me, but for you, right, is going to be tricky. So, mass is simply density times volume. Now, and that makes a lot of sense for very simple problems where you have what we call uniform density. Uniform density is when you are using the same type of material for the entire object, which is what doesn't happen too often, right? You usually use multiple materials. The density of the cell phone is not the same throughout the cell phone. You have the parts where you have a lot of electronics, the parts where you have the battery, right? It's a lot of differently dense parts of the phone. We do not have uniform density. You can also spill some oil into the water. They will not mix. The density will be different in a part where you have oil and a part where you don't have oil, right? So density also depends on the types of materials that are used. And in order for us to capture the change in density, right, we can calculate the mass using density, and we are going to use what we call density function. And that function, the density function, will say if it's just a uniform, like just a number, then the object is of the uniform density. But the object can also be of varying density because the function that we are integrating, right, is going to be called the density function, and that function will determine eventually the mass. So, for our purposes, the big formula here, you will use this again in Calc 3 if you go there. Mass is equal to integral a to b of rho of x dx, and this is mass of one-dimensional object. Think of a long rod of some kind. Train track, right? Yes, it's a three-dimensional object. Yes, it is a three-dimensional object. But when you consider the cross-section of a rail, of one of the rails, right, for trains, and then it's half a mile long, it's negligent. Also, when you're considering the length of let's say a power cable outside stretched between the two power towers, you don't really think about its cross-section being something. You just see the length of the damn thing, right? And you don't even worry about the cross-section because the cross-section is so small in comparison to the length that we can consider a wire as a one-dimensional object. Now, we know that you have to pay attention if you do electrical work, whether it's a 12 gauge or 14 gauge, and then the fuse and all this kind of, right, circuit breaker. You have to take that into consideration, and that's the cross-section. But generally, when you're buying wire and you know which gauge you need, you just worry whether you have to buy 25 feet or 250 feet, which is a single unit of length, right? So this formula calculates the mass of a long rod, and this rod does not have to have uniform density. So it can start with one material and slowly transition into another material. Also, the transition can be very abrupt. In that case, we can use absolute values to glue two functions together, right? Or a piecewise function to glue a couple of functions together. So there are ways for us to mathematically combine multiple densities and multiple functions into a single mass calculation. So I'm going to jump into homework. There are a lot of examples worked out in a book, so you can read that because you know, I hope, all the letters and numbers and stuff. I want to calculate one of the variables. It's going to be 2-second thing. problem 20 has a density rho of x given as a piecewise function, x squared if x is between 0 and 1, and x2 minus x if x is between 1 and 2. What's the mass? Well, whenever you are given piecewise function, you have to integrate each one of these functions independently using the limits provided in the problem. So the mass is going to be integral 0 to 1 of x squared dx plus integral 1 to 2 of x2 minus x dx. So what you see here is that I integrated each piece of the piecewise function independently, and I used the limits provided to me by the function up there. So the first one over here is x cubed over 3 computed from 0 to 1 plus over here we need to distribute, so that's going to be 2x minus x squared, right? So my integral no coughing is x squared minus x cubed over 3 from 1 to 2. Now, to calculate mass, we are going to plug in the limits. So I have 1/3 minus 0 plus, plug in 2, I will get 4 minus 8/3 minus 1, and minus and minus gives me plus 1/3. Like terms, 1/3, 8/3, 1/3 gives me negative 6/3, which is negative 2. So what I have is 4 minus 2 minus 1, which is 1. Unit of mass is gram, and then you use milligram, microgram, nanogram. You use also kilogram, and eventually ton, which is 1,000 kilograms, and so on. What is the American imperial system? In imperial system, what's the unit for mass? Slug. It's about 15 kilograms. So pounds are not unit of mass. Pounds are unit of force, and you calculate pounds when you multiply the mass of the object times the gravity. So if you are measuring the pounds on Earth for yourself and your pounds on the moon, you are not going to get the same answer, because the gravity of the Earth and gravity of the moon are not the same value. However, your mass of, let's say, 70 kilograms on Earth is also 70 kilograms on the moon and the Mars, regardless of the gravity. Mass does not have gravity or any kind of acceleration in its formula. Therefore, mass only depends on density of the object and its volume. So please think about it. If you are to go to Mars, you will still have the same density and the same volume, right? I mean, you're going to lose a couple of months, in trip, right? Because it's going to be a long trip, a couple of years, but you can do it, right? So now we hopefully understand mass, and that's for one-dimensional. You are waiting for Calc3 to do two-dimensional, throw-dimensional mass integrals, and then you can calculate center of mass, which is a really cool calculation, especially for mechanical engineers. You do not want to generate engineer cars with high center of mass, because you would flip it every time you go into the right. Cars that have high center of mass, like SUVs and so on, you can flip them easily. Also including trucks and all of that stuff. So you have to slow down. The next thing we are going to discuss as a physical concept is the concept of work, which is going to be force times the distance. It should make sense. If you said you're doing work, well, you are doing some physical work, which is you are pushing, pulling, or something. That's the force. And then you are going to do that over some interval in space. So it makes sense that force in its basic physical manifestation, work. So work is going to be force times the distance. And it's literally, you're doing the work by pushing a fridge, right? You're helping someone move, and you are carrying the fridge. So you pick up something heavy, and you move it from point A to point B. And you have done work. So moving that object from point A to point B is the distance you cover. And then the heavier the object is, right, the more force you need to exert to move that object around.
That's just referring to physical work, like manual labor. It's not like programming work, right? Like you're not going to calculate.
You are going to calculate the amount of characters pushing forward, the thought progressing, and all of that stuff. So yes, you are. Because look, do you agree that I had to press into the tablet to create W and has the distance, right? So if you are to connect all of those letters and stretch it out, it will be much further than someone pushing a fridge. Because I got like a mile of line, right? A mile of line per lecture, and that's a lot of distance, which is why I'm so fit, you know? There's a lot of, these muscles here. So work can always be calculated as force times the distance. You can always figure out how it translates into the physical realm. Now, what is happening when you are trying to push a fridge or something like this? Let's just take a look at the graph of force in time. So first of all, you're not even touching the fridge yet. Technically, you never touch the fridge because the atoms repel, but let's say you are touching the fridge. Let's say you are sitting on those chairs. You're all levitating, but I'm levitating too. So let's say that at time 0 is the first contact with the fridge, which you are going to push. As a human being, you are going to push with all of the force. It is rapidly going to hit your maximum force output to push the object. I don't care if you're pushing the fridge or pushing something, pushing someone into the pool, I don't care, right? It's going to shoot straight up like that and then peak out, and then you're going to push, but over time, it's going to diminish. Is this a constant function? So I can say that I am always pushing with a force of 100 newtons? Absolutely not. Absolutely not. As you can see, this is a variable force, and I'm going to call that force capital F of x. So introductory physics, it's okay to use W equals F times D because you will either use average force, right? Or you're going to use constant force. Maybe a robot is pushing something and a robot is pushing at a constant force and so on. Humans get either tired or disinterested in helping. So just, you kind of slack off like the other one will be pushing, right? So because we can we get tired because we get, right, we can start slacking off, right? This is not going to be uniform force. Therefore, we have to call for the integral to compute the work simply by saying that the work is the integral of the force. So you are pushing the object in a distance a to b, and you will be integrating the force function, right, in space, in this case, in 1 dimension. So this is your formula for work in calculus, and this should be your formula for work in your analytical physics course, right, where you are using variable forces to move things around. Now, in terms of the force, physics can go in and say, are you pushing or pulling, right? Now we talk Star Wars, right? Force, push, for, pull. It's just a minus sign, right? So which way, the direction in which the force is applied, because you are sitting on the one-dimensional x-axis, right? So you can go to the left or you can go to the right, push or a pull, and you are just going to consider the positive or negative value. Or you can just say, I don't want to worry about the minus sign at all. Just compute, you get a number, and then you say to the left or to the right. Now, what do I have with this? Different forces of the push and pull, obviously. I am going to just make sure that when you are solving problems in physics and statics and so on, make sure that the force applied is perpendicular to the surface, because that is the component that does the work. The rest is waste, which is why the good push needs to be parallel to the surface on which you are pushing. Let me just demonstrate. I will draw a picture of what I'm trying to achieve now with the chair. Let's put a Mother Earth here. Here is a crate. In my case, it will be the chair I'm sitting on. And now we're going to have a person over here. Not an alien person. There we go. We'll put some shoes there. We can put the hard hat there. Smile on the face. Actually, no, it should be a grunt, because this is what's happening. Look at the placement on the arms. It's coming in at an angle to the crate. Now, if there is a lot of friction between the floor and the crate, pushing it this way is not utilizing the strength 100%. Why? If you consider the force at which I am attacking the object, this force has two components. There is a component of the force that is pushing this object downward. Is it? I am technically leaning on this little bit, right? And there is a component that is pushing straight ahead, which is the one that actually does the work, because I want this to go forward. What is this kind of push over here? So what is this component here that it's up to the level where I'm touching? What is this force doing? It's making matters worse. As I am pressing onto the object down, it's equivalent to adding the weight to the object, which adds more friction because the normal force is larger, right? Friction is coefficient of friction times the normal force. So the more of the normal force, and you are adding on it by leaning on the damn thing, you are adding the normal force, you are increasing the friction, you are making the object harder to move. This force, that it's a downward force because I am at an angle, the downward force is trying to bury the object into the ground. Well, it's a solid ground, it's not going to happen, right? Therefore, the normal force is pushing up, creating more friction, creating it harder. What is the correct way to push and pull? To be parallel with, now obviously you can't always do that because it's too low, right?
I can never do that.
Such as like, that's why That's why you are pushing the pencil, right?
Yeah.
But if you are pushing the fridge, you want your arms to be parallel to the floor. Fridge is tall enough, even for you, right? So you want your arms to be parallel with the floor, and then all of the force is pushing forward, and nothing is adding to friction. Nothing is and making your problem. Now, how else we can deal with this? Well, if it's on an incline, right, and you are pushing forward, well, you are pushing the object into the incline. If your incline is at 30%, your arms should be at 30%. This is where protractor gets useful. So imagine that your friend calls you up, like, yo, can you help me with 2 couches down the ramp from the U-Haul truck? And you go, sure, what's the angle of the incline, right? Here you are showing up with a protractor. I got this, right? But you get the idea. So, when you are working with force problems, you have to decompose the force into its components. X and Y component. Y component has the also effects of gravity. X component does not have an effect of gravity. So when I am looking at the problem, so let's go with the fridge over here. And now you are pushing the fridge. A hard hat, don't forget that, and a smiley. As you are pushing forward, you can see that the fridge has the weight pushing down, the same normal force pushing up. They are canceling each other out. Normal force will be creating the friction force, mu kinetic times the normal force, because that is the one that pushes away. But here is the force, and all you need to do is to overcome the friction, and the fridge will move forward. You can increase your chances if you put those little, like a plates, like a cups, or if there are wheels, obviously it's going to go easy. But if there are no wheels, you can purchase those little plastic, they look like lenses, but they're plastic. They're that big, right? You put them under the legs and it can just fly anywhere. Just, flick it and it goes down the... So it's very easy to beat the friction if you have the right tools, right? You definitely don't want to drag a steel something on the concrete, but you can increase the friction, right? A little bit of so it's very easy to worry about the force when you are on a flat, because as I said, you only need to beat the coefficient of friction and you're good to go. Little issues in physics arise when your object sits on an incline, which produces a couple of forces. You have the W force, which goes straight down towards the center of the earth. That's the way the gravity works. That's your weight, which is mass times the gravity. And now the normal force is perpendicular to the surface. Your friction, this way, friction is also on an angle, and you are trying to push this thing up the incline. So you see that 3 out of 4 forces are at an angle, and 1 force is straight down. Now physics teaches you, and statics, to decompose 3 forces, right? Using the, let's say, 30 degree incline. And then you have 3 sines and cosines for each one of these. And then sum of all x's and sum of all y's. Some of you are shaking your head because you've seen this. What you do is you change the incline onto a flat. You put your object there. You put your normal force the way it's supposed to be. You put your friction the way it's supposed to be. You put your force, the incline is supposed to be. And then you put your weight at 30. And then you have to decompose only 1. The same numbers. And then once you take linear algebra, you can learn about rotational matrices. You can rotate the coordinate system. Then you can stuff everything in one matrix and do it without messing anything else. But that's linear algebra if you care about these kind of concepts.
Pretty cool.
So of course it's physics. So when you learn these kind of concepts really quick, the physics becomes a joke. The whole physics. If you learn to observe the formula and the world around you, right? You say, in order for me to do the work, I have to push something the distance. Oh, there's my formula. Work equals force times the distance. Push is force, and how far I pushed it is the distance. Now, the problems that we consider in this class are the spring mass problems. They will also be considered in differential equations, but linked ones. Here we are looking at the object which is either pulled or pushed by a spring. Now, this is a basic mechanical problem. I am going to support you in a statement that this looks completely stupid, right, as a problem. But you have to understand that this problem is actually every problem you have that has a spring in it, which includes the shocks on your car. Because your car is a big weight on top of a spring that pushes against the tire, which pushes against the road. So what is your car? It's this problem turned 90 degrees. There is no difference. Okay, calculation-wise. Instead of you're going to replace your x's with y's. So whatever you learn for this basic problem here, you can use it in your mechanical devices. Now I'm talking to mechanical engineers. Electrical engineers have a very similar situation with capacitors and inductors, but we don't have to go there. We can just stick with a spring. So what I have here is a system where you can calculate the work done by the spring, and the spring, just like a rubber band, is a very interesting creature because it's always opposing what you want it to do. If you stretch the spring, it wants to compress. If you compress the spring, it wants to stretch. When the spring is in its equilibrium position, then spring is happy because it is at its lowest energy state, which is why we all tend to be lazy. That is the lowest energy state for us, right? When we are not exerting any extra work, thinking, or anything, we're just right, like a blob on a rock. So lowest energy state is that equilibrium state, and then what we say states of excitement. If you stretch the spring, the work has to be done because you have to feed the energy in it, and the spring wants to do the opposite. So we can calculate the force of that by constant the spring coefficient K times the displacement delta X. That's called Hooke's law. It's somewhere in your book. Page 466 for the formula, Hooke's law. They just call it Kx. Your physics course is going to call it negative Kx because of the, physics worries a lot about the direction in which the things are happening. And because the spring always wants to counter what you are doing to the spring. You want to stretch it, it wants to compress. You compress it, it wants to stretch. That's why there is a negative in physics. Now, for math, we don't care about it. We don't have to care about it. We'll just compute the numbers, and then we're just going to say wants to stretch or shrink because common sense, right? So your physics classes will be a little bit So stretch or compress. The force f of x will be given there. So work done by the spring. Again, a lot of mechanical devices depend on this. Is going to be work equals integral a to b of kx dx when you plug in the values. Let's take a look at an example of compressing the spring. You have to be a little bit careful because the limits will play a big role in these problems. Limits. What do we have? Force of 10 newtons is required to stretch a spring 0.1 meters. Force of 10 newtons is required to stretch the spring 0.1 meters. Part A, find K, spring constant. People who deal with springs, they can tell you by the value of the spring constant what kind of spring you are talking about. Is it a spring from your pen or pencil that you can easily beat by just clicking it, right? Or is it a spring that is in a shock absorber for a train, right? That needs tons of weight to be compressed, the same amount you compress it with the one finger in your pen. The only difference, they look the same. Obviously, one is much bigger than the other and a thicker material and different material and all that, but they look the same. They're the same spiral, right? Shape. The stiffness of the spring, how hard is to compress the spring, is measured by the constant K. And I can quickly compute that because force equals K. I put delta x, and delta x is 0.1 meters because you stretched it or compressed it 0.1 meters and used force of 10 newtons. So you can calculate the spring constant K as 10 newtons divided by 0.1, and now you have 10 newtons divided by 0.1 meters. You will get 100 newtons per meter as a spring constant K for this particular problem. Now that I have this, I can write the mathematical model for the work done by the spring as 100x dx. So this is my math model. Now I can have a whole bunch of questions. How much work is done to stretch the spring 0.3 meters? How much work is done to stretch the spring 0.3 meters? 0.3 meters is 30 centimeters. If you don't know how long the meter is, my height is 2 meters. I think I'm 198 centimeters, which is technically 2 meters. So what you see here, right, in terms of the length of my height is 2 meters. So half of and then you go 0.3 would be 30 centimeters, which is 0.3 meters in terms of the length. practically almost about one foot. That's what the 0.3 of a meter is. Roughly, not exactly, but roughly. It's close enough. So what do we have? We have the work, and now we are stretching, so 0 to 0.3 of 100x dx equals some number. Right? You will get 50x squared. You plug in the limits, you're done. How much work is done to stretch? I'm going to write this in blood red. To stretch additional 0.2 meters. What are my limits?
0.5.
Nope. 0.3 to 0.5. Thank you. That's the red word, additional. It is already stretched to 0.3. I want additional 0.2, so 0.3 to 0.5. We'll just calculate additional. If you want 0 to 0.5, then you use the previous problem and replace 0.3 with 0.5 to go just a basic stretch. All right, we're cool with that? Right. So 100x dx equals some other number. There we go. And that's the spring. I hope you're not disappointed. That's the work done by spring. You will use the Hooke's law, which is the kx. You will have to use that to figure out the k. And k is, you either figure it out or it's given to you to figure these things. The next concept I would like to talk about are lifting problems. You have all at one time in life picked up a bag or a suitcase. You thought it was full, but it turned out to be empty, and you went, woo, right? And you felt awesome. It's pretty much the same feeling like when you go an additional step that it's not there, right? You're going down the steps or you're going up the steps, and you just, try to have another one when it actually doesn't exist. So it's like, whoa, and you have a complete reset of your system. Yes?
Oh, it's like when you get a new phone and you think your old phone back off, when your new phone is bigger.
There you go. And you go like, whoa. So all of those. So now, when you are dealing with lifting problems, pretty much always you are dealing with picking up the object which is all in one place and you just lift it. This object that I hold is this box or the bleach over here, right? This is all one object and I just pick it up. The amount of work that it's done, which is the energy of the system, is going to be your potential energy formula. Yeah, I know you got the formula sheet, so. No. So potential energy, which is work done going upwards, is going to be mgh. Mass of the object, right? You can lift it or you can't because it might be too heavy. So m, mass, g, you're beating the gravity, height. How high does it go, right? So work, you can think of it as mgh for solid object. Now, generally, we don't use age in mathematics. We use y for a height, right? Because that's the y direction going up. So for our class, actually in physics, you're gonna see energy equals, right? But for our purposes in calculus, we'll say work equals mgy because you are lifting objects up. Now, we don't need any special calculus formula to lift an object that is your backpack, that it's a box, that it's a rock, right? But then you run into those objects that you can partially lift. And the more you lift, the more stuff there is to lift. Yeah, you're all thinking drunk person. Yes, of course, yes. If you ever lifted a drunk person, you know exactly what I'm talking about. Oh, I see we have some experts over here. Good. You need new friends, huh? But what I want to discuss is a chain. Okay? Think about a chain that is, in a spool on the floor, and you pick up the end of the chain and you lift maybe 10 to 15 links and you have no issues because those links are not too heavy, right? As you lift more and more and more chain, more of those metal links are added to the weight of the chain that you are already holding up, right? Make sense? So the more you lift, the heavier the object becomes and harder to lift. That problem has to be solved by calculus because you have the variable weight, right? The variable mass. The more you lift, the more mass is added. The less you lift, the less mass, right? And that's calculus problem because you have a variable function to worry about. So, when you have a single object like this, there is no variable function here. It's the same gravitational field, whether I lift it here or in the back of the classroom. So same g. I can lift it 1 meter, so that's going to be the same height. And this has the same mass. So I just use the basic physics formula, no calculus. If I want to lift a drunk person that is going to be spilled everywhere on the floor, right? You lift a little bit of that person, and then as you start picking up more of that person, it's heavier, right? So the more you lift the chain, the more weight, mass you add, you need variable function. So when we lift variable mass, so add mass with height. An example is chain. We will use physics formula. We go red with this one. This is what you're memorizing for your test, right? Work is equal to the integral c to d. We are going to be now on the y-axis because we are lifting stuff up. So we're going to use c and d now instead of a and b. We're going to have the density function times the length minus y dy. Oh, I forgot the gravity. Oopsie. Right, we need... now, I need everyone to just look for a second into the formula because you all understood when I said MGH. Ready for your MGH? M, isn't that the integral of the density function? Remember from our first integral today? M, G, H. So we see MGH worked in the calculus formula, right? There we go. And that's our formula to lift chain. lift chain. Or a heavy rope, or whatever you are going to lift and add the weight. So now you're going to have a chain that has the density blah blah blah, which will be your mass eventually, and then gravity. You're going to use metric 9.81, or you're using imperial 32.2 feet per second. L is how high you have to go. So if I need to lift a chain, 4 meters up, then it's 4 minus y. Okay? So let me just add that. To lift the chain to 4 meter height, we have 4 minus y as that term. I just wanted to give you an example real quick. A 10-meter chain with density of 1.5 kilogram per meter hangs from a platform construction site 11 meters above the ground. Figure out the work. So 0 to 10, right? It's 10 meters. So 0 to 10, you plug in rho, you plug in 10 inside, and you are done. There are 2 or 3 more concepts in the book. I'm just going to cover one more. It's enough. If you're interested in physics, you pick up the book and you read it. Also, very valuable resource to learn physics are MIT OpenCourseWare. So OCW, you Google OCW and look up their videos that they record in the classroom as professors are teaching physics. It is out of the world experience, right? Better than the drugs, trust me. You go and take a look at those lectures. You can really learn a lot of really learn physics. I never cared about passing a class. That's just, no one cares what you can pass. You pass your course and then you are useless in a field. You are not going to work. You're going to end up in sales. Okay, that's the way it works, right? You can be engineer who barely passed all the classes, and then you're working sales. And then you're going to tell someone that you never use calculus at work. Clearly. All right? So, in order for you to do engineering, you want to be a mechanical, electrical engineer, you have to know physics. If you're a programmer, you have to sit and you have to program every day, because your field is changing most rapidly. All right? Your professional development will never end, right? You have new stuff every 2-3 months. So lifetime of learning if you are computer science, which is why you have insane salaries, like 100K plus, in some cases to start 100K plus. So let's take a look at pumping problems, where you pump the water outside of the flooded basement, or you pump water out of a pool, or you are pumping gasoline out of the conical tank underground, whatever. You are pumping the liquid outside of some kind of a container. So pumping problems. What I'm going to do is come up with the simplest example here, where you have a conical tank somewhere underground, let's say. Now we're going to put the conical tank this way. Generally, we know they're this way, right? But let's say, this is what we have. It's filled with, say, gasoline on a gas station. It has a hole on the bottom, and there is a nozzle connected to the outside, and there is some kind of a liquid inside, water, gasoline. One thing that I need you to understand is that you don't have to do any work. You see that it's in the nozzle right there. It's the same height of the liquid as is in the tank. So thank you, gravity, for that much, right? The formula for work to pump this stuff out is going to be rho g, density of the liquid you are pumping. Clearly, the more dense the liquid, the harder to push it out. Water versus gasoline versus blood, let's say. I don't know, it's a vampire bank of blood underneath someone, so they just, are pumping up for lunch. So the denser the liquid, the harder to push up. We have our C and D because we are on the Y, right, scale. Now we're going to have the surface area, which is right here, is your A of Y. Surface area of the object, which depends on the height, Y. Then you have your L minus Y. Here's your L measured from the 0, which is the height to which you are pumping the liquid. Just like in the lifting problems, you want to lift your chain all the way, to 11 meters up. It was 11, I said 4. Was 4 minus Y? Well, here's your L minus Y dy. This is the formula you are memorizing for pumping problems. Now we are going to need dimensions for the tank. Let's just make anything up. How many meters? 6 meters. What's the radius of this tank? R equals? 2 meters, thank you. What's the height of the nozzle up there where the liquid is gonna? 6 meters is the tank. 10 meters. In physics, it is insanely important to pick your reference point and measure everything from that reference point. Everything is relative except one thing that is absolute, and that is that everything is relative, right? So, relative to you, I am moving. Relative to the sun, we're all moving. So, when you say relative, you have to be careful about your reference point in physics. First of all, relative to each other in this classroom, we are not moving, right? Remember that the planet is spinning, right? The planet is spinning, therefore we are moving because we sit on the surface of the spinning planet. In relation to the sun, in relation to the Mars, the planet also revolves around the sun. So when you say I am not moving, relative to what? I am moving in relative to a lot of other things. In relative to you and relative to the bleach bottle over here, I'm not moving, right? So now, why is that talk important? It's important to set up your reference point for this problem. Relative to the bottom of the tank where I set my 0. Because I can set my 0 on top of the tank, I can set my 0 on top of the nozzle, and then work negative downwards, which would just involve a lot of unnecessary unpleasantries in our calculation. But it's important to understand that these problems for pumping water will be measuring from the 0 up. Is there a project for you in this particular? And the answer is yes. One of my problems is going to ask, if I pick that one, if you have a can of liquid, some kind, maybe you don't like Coke, maybe you don't like Sprite, maybe you like the sparkling water, I don't care. You have a can with liquid inside, you stick a straw, and then you take a sip. How much work have you just done? Now, size of the sip, what is the volume of that sip? Average sip is given, average human sip is given online. Believe it or not, Google it, you'll find it. The average size of the human sip. Why do I want that? Because I want to see what's the net calorie intake. Because you just used some calories, right, through the work to take a sip, right? That sip brought in calories because one can is like 100 calories, 120 calories or whatever, right? So how many sips do you have per? How many calories just to drink the thing minus the calories that are, right, consumed? I mean, calories consumed minus the calories used to consume it is the net, right? But you need to know how much work you did. Oh, that's going to be a pumping problem, right? Because this is technically the can with a straw inside and you take a sip, right? So how tall is the can? How tall is the liquid? How tall is the straw, right? And you can calculate these things. And that's one of the project problems that is in a rotation. You might get it, you might not get it for your final semester project for this course. Very tedious calculations, but you use this formula in there to calculate the applied stuff. And then when someone says, what do you know? Show them that problem. You know that you use like 2.1 calorie to drink 120 calories of liquid, for instance, right? Cool. So now we just need to stuff all of this in here and integrate. Now, rho you will find in tables. They will tell you what the rho is for water, for gasoline, for different types of liquids that you would run in, right? And if you are working at a company that deals with liquids, right, they will have all of that stuff there. So what is my W over here? W equals C to D. Well, one thing that we did not consider here is what is the height of the liquid? It's clearly not full. So let's pick a number for the height of the liquid. 3. And I'm going to say pump all out. If I want to pump all of it out, my limits are 0 to 3 because that's how much liquid I want to kick out in terms of meters. I want to kick everything out. Then I have my rho G, right? If you're dealing with meters, your G is going to be 9.81. Rho is going to be given to you in the table of whatever the liquid is. Surface area. Oh, great, it's constant, it's a circle. Aren't we agreeing that this is pi r squared? So pi 2 squared. That's my AOI. I am pumping it to 10 meters, so 10 minus y dy. This is a very simple integral to solve because 4 pi rho g is a constant. All I need to do is to integrate 0 to 3 of 10 minus y dy and I'm done. Right? A joke, right? If you don't know the formula, impossible. Cool, huh? Do you understand why you can't get the formula for the test? Do you see this? This is like the cheapest possible Calc 1 integral you can get. You are integrating 10 minus y. That's 10y minus y squared over 2, and you stick in 0 and 3 into it. Right? Your Calc 2 is to remember that formula, to set that problem up. That's why you are becoming an engineer. to do that. This calculation, you stuff that into a $300 computer to integrate in 0.6 seconds, and you get a number, right? And no one is paying you to integrate ever. Cool? Last question, last challenge, same problem. I am switching one thing. Pump 1 meter of liquid. What changes in my work integral? We want to set that up and we're done with the day. If I want to pump out 1 meter of liquid, that's what I want to kick out, 1 meter of liquid. What is going to be changed in this formula here? I'm going to keep my poker face because I heard 3 different answers. And when you yell something out, why did you say so? I heard 0 to 1. I heard 1 to 3. No, I heard 2 to 3, and I heard something else. What changes in the integral that you can see, right? The black integral on the bottom of the page. What changes if I only want to pump out 1 liter of liquid? That's going to be... What do you mean, why? What changes?
From 3 to 2, it starts at 3 and you're pumping 1 out to get 2.
You mean from 2 to 3, not 3 to 2?
2 to 3.
Yeah, 2 to 3. That's correct. And you said it too. It's 2 to 3. The only thing that changes in the entire problem is that you are now going to pump 2 to 3, and the rest stays the same. Rho g, we have our 4 pi for the area. We're pumping in 10 minus y and dy. Why is it 2 to 3? It is because there is a liquid already in a pipe, right? So, what am I pumping out actually? I am pumping out 1 meter that is stuck in here at all times. So, I cannot pump 0 to 1 out. Because if I am to pump 0 to 1 out, then this just stays empty over here, right? And then just the rest of the liquid just levitating above, right? It's not happening, right? Anytime you are pumping, this is the first thing to go. And that's the same top over here that is 2 to 3. Bueno? So, the same thing if you are to take a sip of this bleach, right? You take a sip, it's going to go down. The straw is all the way on the bottom. But as you are taking the sip, it's going down. It's not leaving empty space here. So you are not pumping 0 to 1 out. You will be pumping 2 to 3 out. 0 to 2 will remain in the tank. If you want challenge problems, look at half of the barrel sideways. You solve that. I'll give you a little calculus god crown, because it is tricky. I've seen those as a kid. My grandma she lived in a city whole life, but she was born in a village. When I go to my extended family village back in Serbia, I see they take the half of the barrel, right? They cut it this way, right? And they put water or the feed for the animals inside. So say that you have water in this barrel, and you want to pump it out. Well, you want to pump it out on top. going up. You're going to say, oh, it's easy because the cross section here for A of y is a rectangle. Yes, it is rectangle. Go see how easy it is to compute the change on the area of that rectangle. So if you want to challenge yourself and impress me at the same time, try that one when you did basic problems first, all right? And look for the labs on Canvas, okay?